Start with three positive numbers. Take the cyclic sum of each one divided by the sum of the other two. Nesbitt's inequality says this sum is always at least 3 halves, with equality exactly when the three numbers agree. The natural move is to ask the same question for n variables. Wrap the indices around a ring and sum every term divided by the next two. The guess is the obvious one. The sum should be at least n over 2. So you check. N equals 3 is Nesbitt, fine. N equals 4, fine. 5, 6, 7, all the way up to 12, the inequality holds. And then at 14, the pattern breaks. Here's what the break looks like. A specific positive vector of length 14. Plug it into the cyclic sum, and the value sits just below 7. The gap is small, around 3/10,000ths, but it is a gap, and it's enough. So why 14? The answer has three pieces. A flat surface of configurations where S is exactly n over 2. A point on the edge of that surface where the gradient vanishes. And a Hessian eigenvalue that becomes negative at n equals 14. Each piece alone is harmless. Together, they open a way down. Start with the first ingredient. Take a very simple configuration. Alternate two positive numbers, a and b, around the ring. Every term of the sum becomes either a over a plus b or b over a plus b. Pair them up, and each pair is 1. There are n over 2 pairs, so S is exactly n over 2, no matter what a and b are. A whole 2-parameter family of configurations sitting at the conjectured bound, a flat plateau. Now push the plateau to its edge, send b to 0, keep a equal to 1. You land on a sharp object, a equal to 1, b equal to 0, alternating around the ring. Call that point x0. At x0, every denominator in the sum equals exactly 1, which makes the partial derivatives easy to read off. The gradient vanishes. x0 is a critical point, and it sits right on the boundary of the positive orthant. That boundary is the thing we have to stay inside of. Here is the Hessian at x0 for a few values of n. The entries have a clean cyclic pattern, and the spectrum is easy to read. For n equals 4, 6, 8, 10, and 12, every eigenvalue is non-negative. No direction locally lowers S below n over 2. Then at n equals 14, two eigenvalues slip below 0. That is the threshold. A direction v now exists along which S strictly decreases. Let v underscore minus be the eigenvector corresponding to the lowest strictly negative eigenvalue of the Hessian at x0. Step along v underscore minus, and the Hessian quadratic form is negative, so S drops. That is the direction we want. Unfortunately, v underscore minus has coordinates of mixed sign, so stepping along v underscore minus pushes some of x0's 0 slots below 0. We leave the positive orthant, so v underscore minus alone is not enough. We need to combine it with something. Here is the plateau's gift. Call v0 the all ones vector. Along v0, S is constant at n over 2, so v0 is a null eigenvector of the Hessian. Take v equal to gamma times v0 plus v underscore minus, with gamma large enough that every coordinate is strictly positive. The null direction contributes nothing to the Hessian quadratic form, so v still descends. And every coordinate is now positive, a feasible descent direction. And here it is. Walk from x0 along the combined direction v and watch the cyclic sum. Start at 7, dip, rise again. The minimum sits just below 7. That is the counterexample, live. That dip only exists because n is even. Every step of the story used it. The period 2 alternation, the point x0, the pairing of terms on the plateau. So the argument does not carry over to odd n on its own, but it also tells us where even n keeps failing. The same mechanism breaks the inequality for every even n at least 14, 16, 18, 20, and so on. The first odd counterexample is n equals 25. That is your turn. Find a positive vector of length 25 whose cyclic sum dips below 12.5.